Hi everyone, in this series we're going to be exploring a bit of machine learning with neural networks, and in particular we'll be trying to get our network to correctly classify handwritten digits. In this first video, I just want to introduce neural networks a little bit by way of a simple example. Imagine we have two types of plants, one with red flowers, one with purple flowers, and one day we decide to measure the width and length of some of their petals. I'll call these two attributes x1 and x2 for short. Now since we have just two attributes, we can of course plot this data in two dimensions. Looking at how the red and purple flowers have formed two separate clusters, we can draw a straight line to separate them. This is called the decision boundary, and if we get some new data, and it lies on one side of the boundary, we'd predict that it belongs to a red flower, while on the other side we'd predict it belongs to a purple flower. This decision boundary is essentially what we want our neural network to compute. So let's start designing a simple network. It will have two input neurons for the two attributes, and then two output neurons to output the likelihood of the flower being red or purple respectively. We can then connect the first output neuron to the two input neurons, and the strength or weight of these connections will be the values W1 and W2. So then R, the likelihood of a flower being red, is given by the equation x1 times W1 plus x2 times W2. We can then also connect the second output neuron to the two input neurons to calculate P, which is equal to x1 times W3 plus x2 times W4. Returning to the graph, I'll color the region where R is greater than P in red, and where P is greater than R in purple. As you can see, the weight parameters control the slope of the decision boundary. In order to properly separate the red flowers from the purple flowers, though, the boundary needs to be able to shift vertically. Let's go back to our network design quickly and add a bias term to each of the output neurons. We can see that the biases and the weights together give us enough control over the decision boundary to separate the data. However, there's one huge limitation at the moment, which is that our boundary is always a straight line. That's fine for this particular dataset, but let me now swap this out for something that can't be separated linearly. Clearly we're going to need a more complex network for this. So returning to our design, let's insert a new layer called the hidden layer. We can connect the first hidden neuron to the input layer to get a value which I'll call A1 equal to x1 times W1 plus x2 times W2 plus B1, which is of course our old red output value. We can do the same thing for the remaining two hidden neurons to get A2 and A3. Next, we'll connect the first output neuron to the hidden layer, and this will give us an output of A1 times W7 plus A2 times W8 plus A3 times W9 plus B4, and we'll do the same thing for the second output neuron as well. Back to the graph, I now have a lot more weight and bias sliders to play with, but dishearteningly I can still only make straight lines. This is because all we're doing with our network is adding together a bunch of linear equations, the result of which is just another linear equation. So we need some way to introduce nonlinearity. One solution is to use some sort of sigmoid function. The one you see on screen is f of x equals 1 over 1 plus e to the negative x. For this function, small inputs result in an output of 0, while large inputs result in an output of 1. We'll incorporate this into the design of our network by passing the values of each neuron in the hidden and output layers through the sigmoid function. By the way, this is often referred to as the neuron's activation function. So now, changing the weights for a single neuron changes the slope of the activation function, while changing the bias shifts the function from side to side. Coming back to the graph of our network's decision boundary, we can see that the introduction of this activation function has allowed us to create a nonlinear boundary, which means that with the correct weight and bias values, we can now properly classify the red and purple flowers in this dataset. Of course, I'm just changing these weight and bias values by hand at the moment, but the entire point of neural networks is to figure out the correct values automatically, as you can see happening here. We'll look at how this learning process works a bit later on in the series though. For now, the main thing to understand is how the weight and bias values determine which regions of the problem space correspond with which class, red flowers or purple flowers in this example, so that it can correctly classify new data when we don't know what class it belongs to. Remember that we're only dealing with two attributes in this example, which is why we can look at it in two dimensions. If we had a third attribute though, it's not so hard to imagine finding some decision boundary, or decision surface if you prefer, in 3 dimensions. with 4 or more attributes, okay, it's suddenly not so easy to imagine anymore, but the concept remains exactly the same. So I hope this video has given you, firstly, an understanding of the structure of a neural network, with its input, hidden, and output layers, along with all the weights, biases, and the activation function. And secondly, a general way of thinking about what the network is learning for classification problems in terms of this decision boundary. Next episode, we'll begin creating the network in Python. So until then, cheers.